Hello, thank you for taking your time out this day to watch this video. My name is Trent and I am a third year Bachelor of Commerce student at the University of Toronto, specializing in finance and majoring in economics. Today I want to show you something practical. I built a machine learning model in Python that can predict which credit card customers are likely to default before they actually do, and I want to walk you through exactly how I did it and why it matters. Everything you will see was built on a publicly available dataset from a bank in Taiwan, showcasing 30,000 real clients and their real payment histories. Think of this as a proof of concept. The same pipeline applied to your data would be significantly more powerful. So the problem, credit card defaults are expensive between lost principal, collection costs, and provisions. Every default that slips through undetected is money left on the table. The traditional approach is reactive. A customer misses a payment, then another, and by the time the bank acts, the loss is already locked in. Machine learning lets us identify the warning signs months earlier, before the first missed payment, so the bank can intervene proactively, whether that's a targeted call, a reduced credit limit, or a payment plan, whatever makes sense. So the dataset, as I said before, the dataset covers 30,000 clients over 6 months and has four groups of variables: the basic profile information, payment history, the bill amounts, and the payment amounts. At the end, we have the target variable, which asks the question, did this client default the following month? That is the yes or no question the model learns to answer. Before we go into any of the models, we have to look at the class imbalance, which is a prevalent concept in almost all data sets. If we look at the chart, 77.9% of clients did not default, only 22% did. That's the problem. Imagine a model that predicts no default for every single customer every time. That would score a 77.9% accuracy. That sounds good in theory, but it catches zero defaulters. And for a bank, that is completely worthless. And this is why accuracy is not the correct metric to use here. And what we actually care about is recall, which is all of the customers who actually defaulted, how many did we catch? A missed default cost the bank real money. A false alarm only cost a phone call. I built the model to prioritize catching defaults even at the cost of some false positives. So the machine learning pipeline. This is the full process at a glance. So we load and inspect the data, we clean it, and then we split the data set into training and test sets. Then we build a baseline model, tune it with something called grid search, and finally upgrade to a random forest ensemble. Each step builds on the last, and will walk you through each one. So the baseline model. Every modeling process starts with a baseline, the simplest version possible. No tuning, nothing fancy. So the model I chose to use is a decision tree. Think of it as a flowchart the computer builds automatically, asking yes or no questions about each customer and arriving at a prediction. The baseline tree with no optimization hit 71% accuracy, but only caught 41% of actual defaulters. That's nearly 6 in 10 defaulters walking away undetected. This is our starting point. So why tuning matters. This chart explains why tuning is not optional. The blue line is the model's performance on training data, and the light blue line is the model's performance on new unseen data. Past the depth of 5, the blue line climbs to 87%, but the light blue line collapses to 44%. This gap is called overfitting. The model memorizes the training data, every quirk, every coincidence, instead of learning real patterns. When it sees a new customer, it fails. It's almost like a student who memorized last year's exam instead of understanding the material. So depth of 5 is where the model generalizes best. That is the sweet spot in our tuning process. That is the sweet spot our tuning process finds automatically. So next we have grid search and hyperparameter tuning. So grid search finds that sweet spot systematically. A model has settings called hyperparameters that control how it learns. Things like how deep the tree could grow, or whether to give it extra, or whether to give extra weight to the default class to account for the class imbalance. Instead of guessing the best settings, grid search tests every combination and evaluates each one across five different cuts of the training data, 75 combinations, and five evaluations each, which gives us 360 total fits. The best settings found were a max depth of 5 and class weighting set to balance, which confirms that handling the imbalance directly is essential. The test set was never touched during any of this. It stays sealed until the very end. Next, we have the random forest. So a single decision tree is one opinion. A random forest builds hundreds of trees, each trained on a slightly different slice of the data, and lets them vote. Majority wins. It works for the same reason a panel of experts is more reliable than one. Individual errors tend to cancel out, and the consensus is far more trustworthy. I ran grid search on the random forest as well, tuning the same kind of settings. That results in our best model. So this is the model comparison. The baseline tree has 71% accuracy and a recall of 0.41. After tuning, a recall jumps to 0.55, catching 14% more defaulters with no new data, just better settings. Then we have the untuned random forest, which hits 81% accuracy, but recall drops to 0.34. It looks like the best model on paper, but it's actually the worst at catching defaulters. That's the class imbalance trap. So then the tuned random forest is the winner with a recall of 0.59 and an F1 of 0.54. So what this means for your bank. This demo used 20-year-old public data set with 23 variables. Your bank has transaction level data, income verification, and years of history. Every additional predictive variable makes the model stronger. With the 23 variable limitation, 59% recall is the floor. In practice, the model scores every customer monthly and outputs a risk probability, not a binary flag, but a score your risk team can threshold based on your appetite. Catch more defaulters, accept more false positives, fewer interventions, higher precisions. The model adapts to your strategy. So as I stated before, on a 20-year-old public dataset with 23 variables, this pipeline catches 59% of credit card defaulters, which is more than four times better than a model that ignores the imbalance. Every step was deliberate, a sealed test set, cross-validation tuning, and interpretable outputs. With your data, the ceiling is significantly higher.